Okay, this is 7.1, example 3. But before we get to the example, I just want to talk about a formula on your formula sheet. And it's called the growth and decay formula. And on your formula sheet, it's y equals a times b to the power of t over p. Now, a random formula out of nowhere, right? How useful is that? But I think it is important that as we talk about, using these in modeling situations, y is equal to the amount of whatever substance it is after t, and I'm going to put time here because we can do it in minutes, seconds, years, it doesn't matter. A is equal to the initial amount, B is equal to the growth / decay rate. And I just want to talk about a couple of these, a couple different ones. Sometimes we talk about doubling. If something is doubling, then B is equal to 2. If we talk about half-life, which is what this question will be about, when we talk about half-life, B is equal to 1/2. I do want to talk about one that comes up in the notes, though. Let's say an object is gaining 10%. Then what B would be is 1.1. Now, what this number really is 110%. Because if I gain 10%, I still have my initial amount. So if I go to the bank and I put $100 in today, and they say, okay, in a month, I'm going to give you 10% interest, which is fantastic. Do that if you can. Then what's going to happen is after a month, I'm going to have 100 times 1.1. So I still have my 100, but then I have that additional 10%. And, that's going to come up in the notes. So I want to address it, in the textbook, I want to address it here. Similarly, you might have something where we lose 30% each time interval, whatever that is. B would be equal to 0.7 because we have 70% remaining. All right, T is equal to the time, and then finally P is equal to the growth / decay time period. Now, really what that means is, in the example of that money, I said that, okay, I put $100 in today, and then in 1 month I have 10%. That means that it would take 1 month for my growth or decay to occur. And there's lots of different examples. We're going to run into a few as we go through the notes. If you invest money, or not invest money, let's say you put money into a savings account, typically your growth or decay time period is 1 month. You get interest every month. And we're going to work with some of those kind of monetary concerns within this chapter. And a lot of people, and this is maybe my pet peeve, have complained about how math doesn't teach me how to deal with money or do my taxes. And you're right, it doesn't directly because we don't have time for that. But we certainly teach you the math behind those concepts. And there is nothing better than exponential growth when it comes to money. Einstein has a really famous quote about that. I think it's about compound interest, but it amounts to the same thing. All right, let's get to the actual example before I talk all day on this mic. So it has an example or an application of an exponential function. It's talking about some radium-225, and it says that it has a half-life of 15 days. Now, before we go anywhere, I want to write up here that if we talk about y being equal to a times b to the power of t over p, we actually know a few things now. Because it's talking about half-life, b is 0.5. The amount of radium-225 is halving as we go. I think it's radium. Okay, I'm not a chemistry teacher. I thought it might have been radon, but it does say radium there. It says that it also has a half-life of 15 days. So P is equal to 15. Now, it doesn't specifically tell us how much we start with, but one thing that I'd like to just point out is that regardless of what B and P are, if I put 0 in for T, I get B to the power of 0, and I would get that Y is equal to A, which means that my Y-intercept is equal to the initial amount. And that's a pretty important consideration. I think that makes sense. If we don't let the radium decay, which is times 0, that's how much radium we have. All right, so A asks us for the initial mass of the radium-225. We can just track over to the graph, and we see for part A that initially we have 1.0 grams of radium-225. And then it says, what value does the mass of radium-225 remaining approach as time passes? That's essentially a shout out to the horizontal asymptote. And I'm going to write this a bit of a weird way, and I'm going to say that as T goes to infinity, the amount of radium, or our mass, approaches 0. Now, this is a weird concept that it is never actually 0, but it gets real close. And, realistically, or maybe functionally in real life, if we let this radium-225 decay long enough, eventually it will be gone. And, being gone as a science teacher is a bad way of saying that. It will just degrade into kind of lower elements on the periodic table. All right, so B wants us to talk about domain and range, but they've given us a graph for that. The domain is in terms of t, and the variable t is greater than or equal to 0 and any real number. Now, I mean, you could argue that, we're talking about that for infinity, and will the universe be there for infinity? Who knows? But certainly based on the situation, that's an appropriate domain. For the range, though, and they don't really tell us what variables to use, I'm going to use m just because it's talking about mass. And what happens for m is that my mass is less than or equal to 1 gram, because that's where we start with, but then it's always greater than 0. And that's really important, that because of that horizontal asymptote at y equals 0, this amount of radium does get very, very small, but it never actually disappears, which is a very important consideration. All right, C wants us to write the exponential decay model that relates the mass of radium-225 to, the mass radium-225 to time in 15-day intervals. I do not like doing this, but because T is in 15-day intervals, when I put that into my general form, the length of time, or the amount of time for half to him, is a 15-day interval. So if T is equal to 15-day intervals, then P is equal to 1, and I'm going to write beside it 1 15-day interval. Now that's a really important consideration, because there's actually 2 ways of presenting this formula, and I want to talk about both. The first way, which is what they're given to us, I'm going to put the variables in. I'm going to say the mass of radium-225 is the 1.0 times the decay rate of 0.5 to the power of just T. But I'm going to put beside it that T is equal to a 15-day interval. And that basically just means that every time we get, a 15-day interval that passes, we have half as much radium-225. And they put a couple of points on our curve there. You can see here that it's 15-day intervals. When we have one 15-day interval, we only have 0.5 left. Then we have half of that, then we have half of that. So every 15-day interval that happens or passes, we are losing, or basically just, the radium-225 is decaying to half of its original mass. Now, it's not half of 1 every time, it's half of the previous amount. So when I start at 1, I lose half of that to get to 0.5, half of that to get to 0.25, half of that to get to 0.125, and that's why it never hits 0. If you have your calculator, and don't spend a lot of time on this, but take a number like 1, divide it by 2, then divide it by 2 again, and again, and again, and again, and again, and again, and you will never get 0. That is the concept of that horizontal asymptote, that dividing by a number never gets us 0. That's just not how division works. Okay, the only other one that I want to do here, because I think it is important, and we'll see this later on, is that I could also write this as m is equal to 1.0 times 0.5 to the power of t over 15. But in that red equation, t would be equal to 1-day intervals. And both of these equations have their own advantages. The one in black is a little bit easier to deal with, mathematically or mentally, I suppose. The one in red, at least, if I solve this black equation and I got, t is equal to, and I'll try to make it something, let's make it 10. If t is equal to 10, it's way too tempting just to say, it's 10 days. But if t is equal to 10, it's 10 15-day intervals. So that's actually been 150 days. Now, if I were to solve that with the red equation would just spit out that t is equal to 150, which is a lot easier in my opinion, because we're going to use a lot of technology within this as well. Okay, the last part here is that in D, it wants us to estimate, you gotta love estimating, when m will be equal to 1/30. Now, the way that I'm going to do that is I'm actually going to rewrite one of my equations. Multiplying by 1 isn't anything. So I'm going to, or multiply by 1, it doesn't do anything. It's the identity element. So I'm going to rewrite this as m is equal to, instead of 0.5, I'm going to write 1/2, and I'm going to put the power of t there. And the reason why that's beneficial to me is it makes it a little easier to identify that when t is equal to 1, m is equal to 1/2. When t is equal to 2, and I'll do it for this one, m is equal to 1/2 to the power of 2, which is 1/4. And we're going to kind of look at this pattern as we go on. And you have actually examined this type of pattern before. In Math 20, we talked about something called a geometric sequence, which is what this is. This is a geometric sequence when the common ratio is 1/2. And as I go forward in the sequence, each one of these terms is multiplied by 1/2 to move forward. So when t is equal to 4, I have that m is 1/2 to the power of 4, which means that m is 1/16th, oh, not 16, 1/16th. And then finally, when t is equal to 5, I have that m is equal to 1/2 to the power of 5, so m is equal to 1/32. Now, keep in mind that 1/30th is what we're looking for, which means it's somewhere in here. Now, you look at 1/16th and 1/32, 1/30 is much closer to 1/32. So I would estimate that this occurs when t is, and again, this is a guess, I'm going to say 4.8 maybe. The hassle with this is that, again, the common mistake is the students say, oh, 4.8 days. T isn't days. T is 15-day intervals. So the actual time is 4.8 times 15. And I'm just going to quickly grab my calculator for that because 0.8 of 15 is a little bit ugly. And if I do multiply 4.8 by 15, I get 72 days. Now, the question didn't ask for it, but I do want to show you how easy this is to do on your calculator. And I think that's a really, really big benefit to see, if nothing else. So just setting up my calculator here, what I'm going to do is I'm going to put in the equation that we just looked at, which was 1 divided by 2 to the power of x. And I do want to show you that I could do the exact same thing I did on the board. I actually hit the wrong button there. I'm just going to go to my table first. And what I could do is I could plug in values of x. Now, this is actually, I set it up for my other class. The problem is that the calculator's not writing 1/2, it's writing 0.5. So 0.5 is 1/2, then 1/4, then 1/8, then 1/16th, then 1/32. And we know that it happens somewhere in between there. Now, in order to find out exactly where it occurs, we would have to put 1/30 in as y2. When we graph it, we'll see that red line. It's going to be pretty close to the x-axis. But basically, this blue line is the amount of radium we have. The red line is 1/30th. And then what I need to do now is I need to solve for that. Now, I'm not actually sure if it's intersecting on my window because my x-max is only 4. So I'm just going to quickly go to Zoom Standard. Sorry about all the button pushing there, but we'll see that graph again. The blue line is my radium 225. And then the red line is 1/30th. It does look like the blue line goes below the x-axis, but it doesn't. I am going to find that point with second trace intersect. And there's only one intersection, so I can get away with just kind of hitting enter 3 times. And I get my intersection is at 4.9. I said 4.8. So I was off by 1.5 days, which isn't bad for not using a calculator, I suppose. When we do actually look at solving these, graphically and algebraically, which won't be till chapter 8, it's going to be really important you know how to do this graphically. And it is, I've talked about this so many times in class and otherwise, when you are trying to solve this, I'll write that equation. What we just solved was when is 1/30 equal to 1/2 to the power of x. This left-hand side was y1, the right-hand side was y2, and we found the intersection. That's going to be a nice, reliable way to solve anything graphically, which I think has a big benefit for sure. Okay, that's 7.1, kind of that intro to exponential functions. I'm going to put the standard textbook assignment up, but I will have a modified one in Google Classroom.